So these are the 4 class objectives for at least this first half of the class. The first one is to understand the concept of urban hydrology, or how water moves from one location to another, or how much water becomes runoff after a rainfall. Then you also have to quantify certain processes. For instance, you have to quantify how much stormwater is infiltrating into the ground, so infiltration rate. Also, you have to quantify amount of rainfall happens in an area, because rainfall is a very heterogeneous process. If rainfall can vary by time as well as locations, you need to quantify the amount of rainfall for locations. So learn that process. And then at the end, we'll learn about how rainfall intensity can be measured by different techniques. So these are the learning assessment quiz, or the questions. I'll post some of them on CCLE, and you should try to answer some of them at all of those, which will help you for for quiz as well as midterm questions. All right, urban hydrology. Urban hydrology means how stormwater move from different locations. So let's think of why when we need that. The entire class is all about designing green infrastructure. The reason we design green infrastructure is first to decrease flooding, because you don't want the stormwater to flood entire area. And second is to remove pollutants. The first concept is decrease flooding, or decreasing the surface runoff volume. And the way to decrease the runoff is to install this green infrastructure such a way that it removes some of the stormwater away from the overland flow. So you see this picture over here. This is the target, and this is the green infrastructure we design in between, so that some of this runoff that comes here will be diverted away from that runoff. So that means you have very small amount going to the become the overland flow. So one of the design feature is to decide what size of those green infrastructures should be, and those size depends on how much stormwater you are receiving in that location. And that stormwater volume is based on many different factors. Number one is type of rainfall. You got to have an understanding of how much rainfall you expect to receive in those areas which contribute to runoff. And not just because there are lots of rainfall doesn't mean that everything becomes runoff, because some of the rainwater can be removed from the runoff by different processes. So you have to identify those processes, the process that remove rainwater from runoff. So let's say this is the catchment area, and this is you can call it as a collection area. This is all the storm rainwater collection area, and all those rainwater comes in, some of them become runoff, and rest of them will go somewhere else, and we'll understand that process. The idea here is you want to know how much flow rate you are expecting to receive, and what's the peak discharge point. Peak discharge means what's the maximum amount of flow you may receive at any point. If you know that one, you should design the green infrastructure such a way that it can accommodate that maximum capacity. It's the same thing as you hear nowadays coronavirus and flattening the curve. What does that mean is the hospitals should have enough capacity to accept a peak number of patients at any time. This is the same way. We have to design this green infrastructure such a way that it can receive the maximum amount of design flow for that system. So this is the mass balance about where the stormwater coming in, how much rainwater goes where. So let's start with this one. So this is the control volume. And this is let's say the catchment area. What coming in here is this. Anytime arrows goes into the system, that's coming in. So this is input. And so this is the only input. Rainwater is the only way water comes into the area. Let's assume for that. And then there are 3 output. One output is number 1 is runoff. So that is stormwater. So this is what we are interested in, because that's what we need to treat. But whatever comes in, there are some other water will first become infiltrations. So that's I. And some of the storm water or the rainwater can evaporate. And that evaporation can occur through either open area where you have a pond and things are evaporating, water is evaporated because of heat. And also water can evaporate through plants because plants pump those water from grounds and transpire. So that's why it's operationally impossible to distinguish those two processes. So that's why we combine them together and call evapotranspirations. Evaporation is just open water, transpiration through plants. So this is ET. So we account for infiltrations, we account for evapotranspirations, and there are some water that could store in the surface itself. For instance, if you have a pool, or if you have a small depressed area, for instance, let's say there is a hole here. When there is a rainfall, that hole will fill first before there is a runoff. So that we call storage. So storage is related to any open area, any roughness in the surface that will absorb some of the water. So that's the storage. So if you combine those together, so this is all in, this is all out, and this is storage term. And if you reshuffle that equations, runoff R is precipitations minus all these other terms. And so these terms are a function of landscape properties as well as to some extent the design. So the goal here is to decrease the runoff as much as possible. And to do so, we have to also design green infrastructure. In fact, when you think of what green infrastructure does, it actually improves these processes in increased storage. It can also increase evapotranspiration. If you plant lots of trees, that will increase the evapotranspiration. And it can also increase infiltrations. So this is the goal of green infrastructure. So if you combine them together, you can say that some portion of the precipitation will be lost from runoff because of all this process, and we can call that as a beta term. So all this can contribute. We can say that small portion of the precipitation will lost because of this process, and then we cancel that out. We get a factor C, which is 1 minus beta. I mean, this C is called runoff coefficient. Why this equation is pretty significant? It simplifies everything. It says that amount of runoff generated at any area will be a fraction of the rainfall occurs in that area. And rest of the fraction will be lost because of all these other processes. And that's the whole idea of designing green infrastructure, to decrease that C. So the goal of green infrastructure is to decrease that C such a way that only a fraction of the rainfall amount becomes the runoff. And again, precipitation, when I say precipitation, it's called inch. That means 1 inch of rainfall happens in that entire area. If we convert that to volume, it becomes area of that catchment times the depth. So then you multiply, so that's become, so precipitation, which is volume term, will become, or flow term, become intensity times the area. So this is the entire, this equation is something that will come across multiple times. So this is a concept of this urban water hydrology, but we'll see a different form of this same equation a lot of different times. Any question? All right, so we learned that if only a small fraction of rainfall becomes runoff, and that fraction that doesn't become runoff, we call rainfall abstraction. That means that's the amount that removed from rainfall, rest of them become runoff. So that rainfall abstraction is multiple process. As I said, there is infiltration is one process, storage is one process, evapotranspiration is one process, And there is that storage. Water can store in many different forms. In fact, water can store in on the plants just by trapped by vegetations. We call that interception. So that means you can say, after a rainfall, if you shake a tree, you get a lot of water. Those are the water storage as interception. Interception, in fact, a very high amount. If you think of at Los Angeles or any location, first 0.1 inch of rainfall can be intercepted just by plants. That's a significant amount. And then you have to think about the transpirations as well as evaporations. So these are the different processes. Again, I discussed before, all these processes can be improved by using green infrastructure. And this, in fact, that's how we design green infrastructure to improve some of the processes. We'll discuss about very briefly what is interception and depression, most importantly, how to improve those. Interception, as I said, is all about water remains on the leaves of a plant. So to increase interception, you have to have lots of trees. So that means what you have to do is increase density of trees around those areas, density of tree density. And second, not just tree density, different trees can intercept different amount of rainwater. In fact, the trees which has a lot of leaves, leaf density would also trap a lot more water. So that means leaf density also matters. And that leaf density could vary with different types of plants. In fact, if you see, there are two different types of plants we broadly define. Deciduous plant trees have less capacity to retain this rainwater. Again, this is just a concept. There are equations that describe it. You don't need to know that equation, but just know that this equation exists, and I have, maybe those are in the handouts. I don't remember exactly. The second one is depression storage. The reason it's called depression storage is because if you have a plain surface, you do not store any water. But what if I dig it and create a depressed area? So that means now we can call this area will receive, because of the depression, this much water, storm water will be saved, rainwater will be stored. So that's why we call this is depression storage. Just because we call depression storage doesn't mean that flat surface will not retain save any water. In fact, if you have a flat surface which is just bare land, and then you have, let's say you have grass. Let's say this is a grass. Because there are grass, in between grass, there are a lot of water that can stay. In fact, if you walk after rainfall on a grass surface, you'll see your entire feet will be wet. Whereas if you walk on a cement, and that grass species can save lots of or retain lots of water. So that means you can think of surface roughness. Surface roughness. If you increase surface roughness, you will increase that retention by depression storage. Other factor is also capillary. For instance, if you have two different type of soil, one soil is very fine. That means anytime you put a drop of water, this will retain within that particulates. So if you have, let's say, two particles, it can retain water within that by capillary. So these are the different processes that would influence increase in storage. Again, if you think of which one is a bigger factor, depression storage, you are not going to design such a way that you increase depression storage. The difference is either bare land or a grassland. You can have a lawn that will have some extra storage. But interception is very effective. If you see, the range of interception is 0.1 to 0.3 inch. And that's pretty significant in area like Los Angeles, which receive very small amount of rainfall. So that means if you have very small amount of rainfall initially, most of the water will be trapped in the trees. Any question?